Okay, hello everyone, I'm ShengYi Hung and welcome to my talk. Today the topic of my presentation is about ABI stability in FreeBSD. The focus of today's talk will be specifically on the ABI for the kernel. You might be wondering why the word kernel is not exist on the slides or does not appear on the BSD CAN schedule, but it will become clear later on. So let me begin my presentation by presenting the outline for today. For anyone who would like to access the slide before they are officially published, they are available at this location. And let's take a short pause here for about 10 seconds so you can obtain them. Yeah. But I suffer from a problem from PDF LaTeX, so you will see a raw HTML and you have to open it by your browser. Okay, let's continue. First, please allow me to clarify two concepts. The first is what is the ABI and why should we care about stabilize it? And the second is how is the executable format in FreeBSD, that is ELF file format, stores the ABI information. So what exactly is ABI? Before answering this, we first recall a concept of an API, which stands for Application Programming Interface, and API operates at the source code level. For instance, when dealing with a function, the function signature includes the parameter and the return value forms its API. More precisely, the API is presented through the language identifier like int or some structures. So it is its expectation of a symbol. Yes. On the other hand, the ABI or application binary interface functions as a binary label. It determines how a caller organizes its parameter into binary, and then it can pass to the callee. And the ABI defines the layout of data structure in binary, the method of passing argument, and the return value. More comprehensive detail can be found on the Wikipedia page let's introduce ABI concept. On this slide, I have listed several aspects that ABI actually care. First and the foremost is the calling convention that we have just mentioned before. And this refers how structure and data are laid out in memory or registers, then they can pass to the callee. Another critical aspect is syscall interface, which resembles like a function call, but making a syscall requires more effort, like you have to context switch from user space to kernel and then switch back. Like we have systemv ABI actually. And another example are exception handling and name mangling. This is actually defined inside the C++ Italian ABI. And yes, C++ Italian ABI define what structure you should provide for your C++ runtime to enable to handle exception and other stuff. Now, why does ABI stability matters? The most important reason is that not all of the kernel modules are included in the base FreeBSD source tree. There are several out-of-tree modules such as DRM and VirtualBox. Some of these even built using the FreshPkg system. When FreeBSD release maintain a stable ABI, developer of these external modules does not need to worry about the code breaking during the ABI change. This stability allows developers to focus on supporting FreeBSD current without the need of make frequent fix for stable or release branch unless they choose to MFC something that break ABI. This stability also benefit the long-term maintenance costs. If you are enterprise and you are enterprise user, the company that distribute update binary kernel module can do more easily without need to update the unrelated component of just for a simple change. It reduces a step before it reduces long-term maintenance costs by establishing a consensus that long-standing interface should not be changed. Additionally, it makes life easier for developers who can rely on established interface without having to trace the source code or document frequently to determine expected behavior and side effects. And when breaking change do occur, having ABI stable means that changes are more visible, helping developers prepare and adapt accordingly. Now, let's take a look on how a binary format like ELF stores ABI information. There are two main formats used. One is DWARF and another is CTF. Both are utilizing for represent ABI-related information, and in FreeBSD, CTF have been in use within the kernel for many years. Let's begin with DWARF. DWARF split information in multiple sections to capture both language-specified and non-language specified information, and compass API and ABI details. The DWARF specification is extensively around 200 pages. For example, the debug info section holds DIE. It is an abbreviation of debugging information entries that contain information about scopes, file, line number, and type of information for the symbols. The layout of debug info is defined by another section called debug abbreviation. The debug string section acts as a string pool. Meanwhile, debug frame and EH frame provides information used in stack unwinding and exception handling for C++. There are also other sections dedicated to specific use case. Let's talk about another data format, the CTF, or compact type format, can be seen as a minimalized counterpart to DWARF. It is designed to represent C type with very compact storage. CTF only retain type information and exclude elements such as stack information, scope, file path, and line number. This is unneeded when comparing type. Fortunately, the FreeBSD kernel includes embedded CTF data because there is a concrete consumer for it, that is the dtrace. Now let's dive into some more practical aspect. And how can we ensure or enforce ABI stability? The first step is to have a tool that can detect ABI difference so we can assess whether any break change are permissible. For that purpose, I introduced a new tool called CTFDiff. I have also prepared a page that implements it. So yes, overlay. And so what exactly does CTFDiff do? The tool makes the tools takes two ELF binary as an input, and parse their contents include header, then extracts the CTF section. Note that CTF section may be complex use zlib, so we need to handle it carefully, appropriately and carefully. Once we extract the CTF data, we parse both type and symbol information. Symbol could be function or some variable like static variable or global and static variable in C. If a symbol with the same name exists in both binary but have different signature, that is a sign of an API or ABI difference. In CTF, the type information is categorized into several groups. Each type information has its entry, and each entry representing like a structure or a function has a unique ID. The ID is beginning at 1, and they are implicitly assigned based on their order of in the CTF section. Like if this type of information is the first element of the CTF section, then its ID must be 1. Let's talk about each type specifically. Base type contain metadata such as size and encoding. Encoding means little Indian or big Indian, and the offset. Qualified type like const or pointer reference. Another type for example, a pointer to an integer would involve two type entries. One is for the pointer and one is for the base type. And the pointer will point to the base type. So when you are parsing the type information, you are doing in DFS. And structure contain field information with associated name, field name, offset, size, and underlying type the underlying type information of each field. For example, a structure contain a pointer to an integer would point to the pointer type entry, and the pointer type entry will point to an integer entry, so it represents a full structure. And actually, the dwarf follows a similar design. And then function in type information in CTF indicate type def or function pointers. These entries record the return type, argument count, and argument type. Unions are treated similarly to structures, but their sizes are calculated differently. Structures are sized based on the sum of their field size and padding, which unions are sized based on the largest field plus alignment requirement. For the user of CTF, the focus is usually on comparing size instead of manually create an entry, so it does not matter for us. There are actually some edge cases in CTF. For example, type ID 0 is reserved for VARG, which cannot be resolved at compile time because we cannot get the value type information of a VARG. That makes sense. This requires, and because this VARG type ID 0 is not exist in the type information entry, so we have to add a dummy node for VARG to indicate it is a VARG. And another corner case is circular reference. For instance, you might have structures A and structure B where A include a pointer to B and B include a pointer back to A. That can be defined by it can be compiled in C, and yes, you can use forward declaration to achieve it. This kind of cross-reference requires careful handling to avoid infinite loop. A common case is a linked list which a structure pointed to itself. The third issue involves performance optimization. Actually, illumos also has a CTFDiff tool, but it is but I'm not sure if it has been used for test a large binary like kernel, because in my experience, if we don't cache the type pair, if we have visit them before, that will cost about 30 seconds to compare to kernel binary. So, but with the caching, it takes about 2 minutes. So then yes, so there is a difference between both version of CTFDiff. So, and there's another question. Yeah, why not we just use the illumos or CTFDiff? First, we actually need a tool to be more user-friendly and capable of supporting additional output format. To achieve this, we had to integrate libxo. And adding this dependency would make upstreaming difficult because the illumos actually does not have libxo in my memory. I'm not sure. Second, I redesigned the normal output. That means if the CTFDiff is configured without libxo, be more like a normal diff. Yes, the diff program. So this is not the case for illumos CTFDiff. And third, because I love C++, so I want to re-implement it using C++, but this is just kidding. But the actual reason is for the cache mechanism which I just introduced. It is very easy to using a std map and std set, but in C we have to implement the whole hash table or something. And there is another thing, because we have said before there are many types. The pointer each has its entry, and in my implementation, I actually abstract each type as a class, and I use RTTI information, that is the type ID, to compare if they are the same class. I think it's more elegant. Yes. So it's demo time. It is a little bit small. Is it larger enough? Okay. Okay. And there is, for CTFDiff, we actually want to compare two binary, right? So we have two source code, one is A.C and another is B.C. So we can see the content of A.C and oops. So the oops. On the left-hand side is, I don't know why there are such imbalance, but yeah, let's continue. The left side is A.C, content of A.C, the right side is content of B.C, and we can actually discover there, for example, there's var A half, so there is a symbol in A.C called var A half, and there's a symbol var B half in B.C. So the intended behavior of CTFDiff would be A.C will exist. It will show A.C in A and B.C in B, and yeah, and then another variable var above same and var above same have the same type information, and yeah, so it should not appear on the output of CTFDiff. And that's the next symbol, the var buff_diff and var_buff_diff on two sides. The left-hand side is int, and right-hand side is the double. So it should be the output of CTFDiff should be we have these two symbols, but these two are different. And for function, yes, it's just function for the same case, but it should be the same behavior as the variable. There is a function a have and function b have. Let's just like var a have and yes, so let's just see the output. And currently, the CTFDiff cannot generate directly by the compiler. It's actually you have to generate a DWARF first, then use CTF convert to convert a DWARF, the ELF file with DWARF to a ELF file with CTF. So we can see the make file. It's actually built, and yes, you have to pass -g to the CC to generate the DWARF entries, the DWARF sections, and you use CTF convert. And -l actually means it's just a label. It does not have special meaning. Like in FreeBSD, this label may be FreeBSD 14 or FreeBSD 15 instead of FreeBSD test. So I think there is no any intended meaning inside. So you can just type whatever you want, and use CTF convert to convert a binary from a DWARF binary to a CTF binary. Then use CTFDiff. Okay, so we have converted two binary A and B, which has the CTF engine. Oh, there's a thing that the CTF convert actually can only handle a single compilation unit. That means you need another tool to create full CTF entry for dice, or this is called CTF. CTF merge. So you have to, in reality, FreeBSD actually create .o and use CTF convert to each .o and use CTF merge to generate a final result for .ko or something else. So there is a CTFDiff A, B. Yes, here's the output. And just as intended behavior, it is the function A and function B there are different symbols. So the function A actually appears in the left-hand side, and function B appears in the right-hand side. And function buff_diff means they are same symbol, but they have ABI difference. So yes, it output as the screenshots. And then we can go back to okay. So the current status of the CTFDiff is as following. First, I'm looking for the review of the patch we had showed before. And additionally, because CTFDiff link libctf, which is licensed under CTDL, so we must decide on its licensing. We can either adapt it as a BSD and put it under user.bin, or keep the CTDL license and put it under contrib CTDL. And Warner actually shared his thought on this, and I have decided to keep it as a CTDL license binary. Yeah. Regarding libxo support, around 6 months ago, I discovered that libxo makes external C guard, and which prevent us from using it in CTFDiff, because you know CTFDiff is C++, and if you don't use external C guard, it will doing name mangling for the C++ symbol, but so it fails on link. And I submit a patch to upstream, but I think they haven't released a new version of libxo, so they haven't upstreamed it to the doing a vendor import to FreeBSD. So I'm not sure when will they do this? If anyone can help expedite this process, that would be very great, appreciated. Yeah. And the most thing is the current output of CTFDiff is not yet detailed enough. As we have said before, that he can actually output the difference, the ABI difference, but where is the difference? It does not elaborate on this. So I would edit after the libso is imported to the FreeBSD base. Yes. So now we have had a tool that can efficiently track ABI difference between binary versions. The next question is, how do we integrate this into our CI workflow? Here is my proposed workflow. It is patch-based, which when a patch is MFC from the current to stable, that is merged. Just for example, stable 14 branch, the CI system build the source tree and store the compiled output in user object file or another directory. Then it download the release table like 14.0 and compare the new kernel and OKO module against it using CTFDiff. Finally, it generates an ABI difference report. Yes. And this process actually also works on user space binary since there are also ELF files with optional CTF sections. The only additional space is downloading the user space table instead of the kernel table with kernel stuff. Yes, and for the step 2 to step 4, I actually have a script to automate them. Let's move on to another demonstration. Oh. And here is a ctfdiff.sh. And because there are multiple, I don't know, 100 or tens of kernel modules, so the output will be very long, so I redirect to another file. Oh, I think I missed some parameter. Let's just, so the menu of the ctfdiff.sh is as following. You can change the architecture if you are x86 or ARch64, and you can change the version of the base, like you are 14.1 release, or that will change the remote table where to fetch the remote table. And -d, you can change the where is the master side to download the table, and -o means where is the object root, like in user object, user src, and -k means it will change the kernel config, which used to compare the difference. And yes, there are 3 types available. One is base, one is kernel, and lib32. Let's just try kernel. No, I don't have generic compile, so I can use the -k generic no debug, and we'll start download, but the output will be massive. So I redirect to another file. So let me just wait it for download. I think it takes about 20 seconds or 30 seconds. Oh, down. Then we can see the output. Yes. Oops. And it's actually lists all ABI difference, and it will tell you that something on the top is cut. But yes, you can see his CTFDiff.sh actually compare each .ko and actually output the ABI difference. But the output result in here is much more meaningless because I'm using 15 current and the binary I download is 14 release, so the ABI must be changed and have many change. So yes, it's just a quick demo. And we can, I think we can try to pick a random symbol and to verify if it is correct. For example, I remember. Oh, this one, okay. Let's pick a random symbol. It's inside main.ko. Oh. Oh, I choose this symbol, and yeah, and can and we can trace on this symbol first, maybe here. Wait a minute. Is there any change in this file? No, so the change may be inside, and maybe this one. Is this the same? Oh, these are same. So maybe on this. Yes, I think it's over here. The mem open actually takes a thread as a parameter, and when I compare the result from the using magic diff, that is actually the git diff, and it shows the short thread changes because their signature is mismatched. The upper one is yes, the upper one is /rl-q-entry, and another is void pointer. Yes, that is actually a change. Yes, so yes. So let's continue. Demo finish. And until now we are talking about API, and what about API? And actually, CTFDiff inherently performs some API checks since it's compared to type the name of two types as part of the symbol information. The difference in the type name can be detected. So if the type name is different, or yes, if the type name is different, that's actually a API incompatible. Yes. So API difference are also caused naturally. Look, yes. And there are some future works, and the first question is, can we catch the issue when we are developing FreeBSD? And yes, you could. Yes, of course. The answer is of course you can. You can run the ctfdiff.sh manually by yourself, and you can get a detailed ABI difference output. But this might be slow but efficiently for practical use. Actually, let's make the problem more simple. In reality, the kind of changes that breaks ABI or API typically those that affect publicly visible symbol in KO or DISO. That means if a symbol is public or should be viewed outside of the module, the KO DISO, then it needs to be taken care. Then such a hidden symbol in the module we don't have to take care. So therefore, we actually need a mechanism to monitor change to public interface. So that means we want to introduce module level visibility in C. The visibility in C is originally designed for a minimal unit of C, just like the compilation unit. That means the .c file, it will generate .o file. The visibility is actually for .o file. Yes, so it can, if you type static, it actually define if you have a static variable, that means you cannot, this symbol cannot be viewed outside of this compilation unit, but instead of that module, like .o.ko. Yes, it is just like Rust. We have pub and pub create to define the visibility. So how can we implement it in C? So one approach, but maybe over engineering stuff, is we have LLV and LTO visibility, so that we can use the LTO visibility that have hidden or public, and we can take the hidden and public stuff on that, so then we can know the visibility in the module. But this is just as I say, it is a little bit over engineering because we have to compile all of the binary into LLV and IR bit code instead of the x86 binary code. So, and then we have to link libLTO to our kernel. But yeah, so that is a little bit over engineering, but it's also a viable method because the LTO visibility is actually implemented as an attribute in CLAN. So it is the nature mechanism in LLVM. Another approach is CTF. We can extend the CTF standard to then extended CTFDiff or add a linter. So if we add so we can add a bit or some field in CTF for the symbol, then we can take the symbol with public, private, or hidden visibility. Yes, the upper method for LTO is supported by the compiler, but need to do a lot of modification of our kernel. But the lower one is in opposite, that does not have any implementation for the compiler. So we have to make modification on compiler side, yes. So I have a simple conclude about ABI and API is do we reach out a good answer about ABI or MPI stability? The answer is not, but the best I can do is to provide tools to like a linter, like CTFDiff, and a mechanism on CI and some SOP to help detect and enforce stability. But actually achieving true ABI-API stability requires the collaboration and on all committer and develop. That means we have to define some rules to define some rule to regulate the ABI and API, and all of the committer and developer should follow it. So then we can have a stable ABI and API. So okay, it's my talk today. Thanks everyone listening. Is there any problem? There is no mic. Eh? Yes? Yes, I will repeat the question if there is no mic.
Check.
Oh.
So, apologize if you covered it already, but does this tool show a difference, if there's any difference in the CTF, or if there's an actual ABI change?
We define to define an ABI change, that means we have some that is underlying a same symbol. So the same symbol in C or in ELF actually means the same names, and the same names has different type information. And so for me, the ABI difference actually is for the simplest ABI change actually means only the type of information difference. But I think the most precise definition of ABI change is that we have to include what I have said before, the public and private information. And if the function or symbol is public and it has some change of the type of information, there should be a true ABI difference. Yes.
So in the example you gave, so I guess this is extending what Christos asked, but in the example you gave where you have that struct thread field, the type of the field changed, but the size didn't, right? Because it was a pointer before and it's a pointer after.
Yeah.
So all the other fields around it don't move, right? So if you're DRM kmod and you're accessing fields from struct thread, it's okay to change or to replace unused fields as long as you don't move other ones around. I think to detect the kinds of ABI changes we care about, you might need to be more precise.
Yeah, but I don't know how you can have a good heuristic that an arbitrary void star is an unused padding field. I mean, you can pattern match on the name of the field member maybe, but otherwise they just look like other pointers. It's kind of hard for an automated way to know that this is a padding field. It's okay to change the type versus not.
Yeah. And actually, I think for a tool like CTFDiff, I provide I just want to produce a detailed report, and we can provide more option to avoid some edge case, like there is one option that my CTFDiff implementation we can how do I say? We can ignore all of the const. So if a structure has if a type is const A and const int, and after change they become int, we can omit it. With this option we don't have to output it in the CTFDiff. So we actually can have many options like this to provide more fine-grained or detailed report, or yeah.
I guess I have one comment. ELF does have a notion of visibility in ELF itself. So you can mark a global symbol, a symbol with global binding as hidden visibility, in which case it's private to kind of the containing DSO, like the shared library, like we use this in libc. We have a little wrapper in ctfs.h. It's another like attribute you would do as compiler, but you don't have to do an LTO visibility. It's actually an ELF itself. I don't know if ELF visibility survives transitioning to CTF. I don't know if CTF has a way to encode it, but in ELF there's already a way to do it and a way to do the annotations in the tree today.
Oh, okay. I am not actually. I don't actually does not know there is a module level definition, module level visibility in ELF.
Native to the language, it's clunky still, but I mean, and if you would have it native to the language, it would be some kind of clarifier on the type, and an annotation like __ hidden that we have in ctfs.h is functionally equivalent to what you would type anyway. But there is something in ELF for this.
Okay, I will take a look.
I talk about it in my next talk too.
So maybe I missed a little bit, so apologies in advance, but as I understand it, the usage model is like you have two kernels that you compiled separately and you compare them. But I think the useful model, at least for me, is, okay, I have DRM kmod modules and I have a kernel, and I want to look at all the types referenced by DRM kmod and see if they match the ones in the kernel. So if the definition of struct thread in i915kms.ko is different from the one in the kernel, then I know they're not compatible, and so I shouldn't load it.
That's a very different
And the problem is that the first original design for me is that if you only have type information, that is not enough. There's no meaning, because you have to bind the type information to a variable or a function, then the type information will be meaningful. Like if you don't have any definition you don't have any definition for the type, that just, for example, it's not, this type is not used in a kernel module, but so if the type is not used in a kernel module, that will be useless because there is no target we can compare. So if, for your question, if there is something extern symbol in DRM that's the definition resides on the kernel, then we can do a comparison. We can do CTFDiff between kernel and DRM.ko because this symbol actually exists.
It's just a very different question than I think what you're trying to do. This is a more straightforward diff of the same thing. I don't know if CTF has it. DWARF has enough stuff so you could look at an undefined symbol from DRM KPI, see when it's called, see the arguments passed to the function and the types of those, then like find out those types, then go find the same function over in the kernel, look at its argument list, find those types, compare those types. You don't even have to match the names at that point, but that's a lot of stuff to write, and like that's a lot of work.
Yeah, but then, but it's easy because, as you said, there's types in the kernel where we don't care if they change, right? Like, so if I take two kernels and compare them, then
well, so that's a larger discussion about which parts of the ABI become stable versus not. So like one of the things you actually did talk about it with visibility. It was one of my questions is you kind of want a system where you take like public symbols that you export and the types associated with those, and you kind of build a dependency graph, and you paint all those types, and the type that doesn't get painted, you ignore, you don't care. Because I might have a private struct foo whatever inside my .o file that I don't export anyway, and so I actually don't care if that type changes. But I mean, I think that's you're kind of already there with thinking about public versus global.
Yeah.
But I think the issue with doing that, I think, is it limits you to whatever DRM uses today versus trying to think about a change in an ABI that maybe DRM doesn't use today, but it might still use in the lifetime of that ABI change existing. Like a newer version of DRM that was still built against the older kernel might break on the newer one, sort of thing.
You have to fix one of the versions of the thing that you're comparing.
Yeah.
Two versions of DRM versus one kernel, or two versions of the kernel versus one DRM.
Anyway, it's a good, useful step, but the policy parts of what you decide to actually be frozen is a complicated problem on top of it. But it gives you the data to start thinking about the policy. Right now, we don't really have enough data to have good decisions about the policy, except I know there's big, scary things where we can't make it work feasibly. But aside from that, I don't know. Yeah, we are hugging the mic. Who else wants the question? Warner's coming over here. He's gonna walk to the mic.
I was just going to come to the mic. Yeah, the thing we want is, I think, closer to what Mark wants. Not a CTFDiff per se, but a CTF compatible. Or, show me the incompatibilities between these things. Or show me these changes with the set of heuristics, masked out. Show me the changes that change the offsets of anything. Show me that, we can have that list of things that we're interested in so that, we don't accidentally introduce these changes. Even if we just said, hey, these two structs are now different and have different offsets, that would be hugely useful, even if we don't solve any of the rest of the problem, because that's 99% of why DRM KMod breaks.
Or VirtualBox.
Or VirtualBox.
In favor of this approach is at least you're diffing the kernels. Otherwise, you have to start comparing every possible KMod that might be sensitive, and like there's all these in-way comparisons. If you've broken any of the possible KMods we care about being compatible, and if you're only comparing the kernel artifact, you're kind of accounting and covering the set of possible KMods, including KMods you may not know exist because they're private to somebody's company, sort of thing. Yeah. So I can see why that's a useful thing, but I think that's a harder question to answer, and this is a pretty good approximation. It's probably easier to implement.
And
No, it's okay.
And if we compiled DRM KMod against two different kernels, and we
Yeah.
did the diff, would that tell us the things that change? The same version of DRM KMod, so if you compile it against the same kernel twice and do the diff, it should be nothing. And then if you compile it against a future kernel, you could take those two KMods and maybe come up with something reasonable that's not a lot of noise, that we could start to use your stuff right away, which is what I've been racking my brains the whole time you've been talking, trying to think, how can we start to use this? And I think that's probably the easiest thing. So if we could get a demo or something of that.
Okay.
I mean, if the test would be to take DRM KMod and compile it against 14.2 and 14.3 and tell us what the diffs are.
And we know there's some. We know it's broken. So just
No, okay.
they are. We have some good guesses.
Yeah, tell us what we broke.
Okay.
So if we could get to that point and get to that with the scripting so that we can, have our golden artifacts somewhere, and then we build the new tree, we could do the meaningful compare to see if we've broken something. And then that might be how we approach it. We don't have to do the set of all possible things that might be in use in weird companies that don't tell us, because we don't care about them because they don't tell us. Right. But we do care about DRM KMod, VirtualBox, and a couple other.
I don't think VirtualBox is fixable. Too many things that you
Well, we would know.
would know.
VirtualBox doesn't use that many
Yeah.
things. It's just a few VM.
Yeah, but that's the worst thing.
But we would know. We don't know now.
Yeah.
And You know, for DRM kmod, I know it's possible to fix because I fixed it a dozen times in the 12 or 11 time frame, because it would break, and then I would go and find, oh yeah, you moved this around, that's stupid, you need to do it this way. Short of completely rewriting Linux KBI, or the Linux KPI stuff, you know, we're not going to change that because it's all inlined, and all the offsets are encoded in the clients.
We need a picture, other people get a chance because we're already 5 minutes over.
Okay.
Three of us have talked.
I think DRM is not a good example because the API in Linux kernel is much more mess than FreeBSD one. So Linux KPI is much more, so yes, I just want to maybe DRM is not a good example, but VirtualBox must be.
Yeah. So, anybody else? Can I?
So more about the tooling you've built than about how to use it. I noticed that when you did the demo of how to do the batch diff, you spent a while digging down into the guts of a symbol that had changed.
Yeah.
How hard would it be to just give a report of this symbol changed because, you know, this argument points to this struct which changed in this way?
Yeah, so I've mentioned in my presentation, I just there is a future work is waiting because I want to have a detailed output, that's right, but I'm waiting libxo to upstream. Yes, then I can leverage the libxo to do formatting, then I don't have to do multiple works. Yeah. Is there any question? No? And thanks, everyone.